Hi, so today I want to talk about section 5.5 in our textbook, which is the bane of a lot of people's existence, and that is the concept of friction. Friction applies to just about everything that happens in our world, whether it's stationary or moving, and it basically talks about a force that moves to resist motion. A force that resists motion. Now, before I want to get into 5.5 friction, I'm going to go back. I want to take up a little bit of homework from the last night's work on 5.4. I apologize for not getting it posted in time. I put the announcement on the hub, and then I forgot to post the video in the hub. So I want to start by looking at the one question that was posted from page 1. Sorry, I got the wrong page here. Page 165, which is the standard elevator bathroom scale question. You see this in every physics course, and you'll probably encounter it again if you take physics again in the future. For the life of me, I don't understand why people would have a bathroom scale on an elevator, but if you can imagine being in an elevator, there's your bathroom scale, and there's the person standing on the bath. There's the elevator cable. Okay, so there's what this whole question is about, and this is a huge question, and it has a lot to do with understanding that concept of normal forces. So if I say, what are the forces acting to that on that person at any point in time, whether the elevator is going up, down, whether it's stopped, whether it's accelerating, whether it's decelerating, whatever it's doing, there are only two forces acting on that person. That is the planet pulling them down and the scales pushing them up, the bathroom scales. And those bathroom scales here, we're going to pretend are Newton scales, right? Actually, no, I'm going to use regular bathroom scales that have a capability of measuring mass in kilograms. And from there, we will look at the forces acting on this person. So the question says, what is the normal force acting on this person if the elevator is stopped? So if I was to draw the free body diagram, so this is question 1 from page 165. Okay, if I was to draw a picture of this person for a free body diagram, I would say there are two forces acting on that person. One is the scales pushing up, one is the planet pushing down, pulling down. Now, as the planet pulls down, what's creating that normal force? Well, it's the scales. Okay, it's the force produced by the scales themselves. Now, the reading on the scales is how much force the scales are having to apply. So this is equal to the scale reading. Okay, so that's what's going to read on the scales. Now, if the person's in an elevator and they're not moving, that means acceleration is obviously 0. Now, if I was to look at what are the forces acting here, we're told that this is a 70 kilogram person. And the question is, what will the scales be reading? Okay, so notice that the scale readings are going to change during this question, whether the elevator is moving or accelerating or changing its velocity at any point in time, the scales will increase. And we know if you're in an elevator and you close your eyes for a minute and the doors close and you're standing there, but no one's pushed a button yet, so the elevator hasn't started to move, if somebody hits a button and it starts going up, you know it's going up because you feel a bit of extra pressure in your knees pushing you up more than you were being pushed up before that button was pushed. Or if somebody pushes the basement button when you're standing there and all of a sudden it starts to go down, you feel a little light in the knees. Those scales aren't actually pushing you up quite as much as they were before. So we're going to see that the scale reading is going to change here. So if I was to do my F net statement here, I know that my F net here is MA, which is 0. Because there's no acceleration, the elevator is stopped. And the two forces are FG and FN. Now I know that my FG is always mg. Again, because we're on Earth, we don't have to use that big fancy formula. You can if you're really dying to use it, but me, I don't prefer to do that. So if I do my 9.8 times 70 to find the gravitational force acting on this person, it is 686 newtons down. Okay, so there's my gravitational force. Now, most of us would just look at it and say, okay, obviously, if Fg is at 686, Fn must be 686. But let's just go through the formality here of doing the math. So if I know that Fnet is 0, and it's equal to Fg, negative 686, plus Fn, I take my negative 686 across to be positive, and I know that my scale reading is 686 newtons. Okay, so there's part A of the question. Okay, part B says, okay, let's assume that you're now in the elevator, and the elevator is moving up at 10 kilometers an hour. Okay, constant speed of 10 kilometers an hour. Bing, 17th floor. Bing, 18th floor. Bing, 19th floor, right? Constant speed going up. Now, if I look at my free body diagram of this person now, oh, look at that, it's the same thing. There's only two forces acting on this person, Fn, Fg. We already know what Fg is because his mass hasn't changed. It's still m times g, so it's still 686 newtons down. Okay, but now I'm moving up at constant speed. Oh, but the acceleration is still 0. So if the acceleration is still 0, I can see that all the math up here still applies, because Fnet is still 0. Fnet is ma, which is 0, which is Fg plus Fn. Fg hasn't changed, it's still minus 686, and my final answer is still going to be a scale reading of 686 newtons. So if the elevator is going up at 10 kilometers an hour or down at 10 kilometers an hour, so long as there is 0 acceleration, ma is 0 and Fg is equal to the negative of the Fn, or Fn is equal to the negative of the Fg. Now things change here pretty quickly as soon as we start accelerating. So it says the elevator is at the top floor, we're in the penthouse, and now we're going to start accelerating downwards. Now notice that at one point in time you have no speed, and then seconds later, let's say you're going down at 10 kilometers an hour. What had to happen in that time period was I have to go from 0 to negative 10 kilometers per hour, whatever that is in meters per second, 2.8 meters per second. Negative 2.8. Right, so I've changed my velocity from 0 to negative 2.8. Change in velocity now tells me there was acceleration. And that's what's going on here. So if I look at what's going to happen now, I still have same free body diagram. Here's the person in the elevator, still standing on those scales. I only have two forces acting on this person, the planet, and the scales. And I know that the Fg is still mg, which is still negative 686 newtons, or 686 newtons down. And Fn now is going to be calculated. What I know is that there is an acceleration of negative 2.0 meters per second squared. And the question is, what are the scales reading now? Now, if I can just slide this up a little bit, my Fnet is equal to ma, which is equal to Fg plus Fm. Ma is the mass, 70 kilograms, times the acceleration of negative 2.0 meters per second squared. My Fg is negative 686 newtons plus Fn. So Fn is now equal to, take my negative 686 to the other side is plus 686. My 70 times negative 2 becomes negative 140. And notice that my Fn, my scale reading now says 546. It has to say positive. You can't have bathroom scales giving you negative answers. That's just, Einstein would have issues with that. All right, so the normal force now, notice that your weight changed. Remember, weight is Fg. Weight isn't your mass. Weight is Fg. Oh, but Fg didn't change. I'm still actually weighing 686 newtons. However, the normal force here, which it's telling me is my apparent weight. It's telling me what I think my Fg is, but that's only because I have a acceleration. The acceleration is going to change the relationship of those forces because the acceleration has to factor into this. And then D says, okay, we're going to have a real problem here now. The elevator cable is going to snap. Now, when the elevator cable snaps, there should only be two forces acting on this person. Now, some of you are already probably saying, if the elevator snaps, that floor isn't pushing up on you anymore. That set of scales isn't pushing up on you anymore, because my acceleration is now going to be what I would expect it to be for an object in free fall. And I know what my FG is. 686 newtons down, or negative 686. And now if I do my F net equals MA, which is equal to FG plus Fn. Right, my mass is 70 kilograms, times my acceleration, which is now negative 9.8. It's going to be equal to my gravity, which is negative 686, plus Fn. Right, now, if I look at what my negative 686 comes across as plus 686, my 70 times negative 9.8 is negative 686, equals force of the scales, and the scales are going to tell me I have no weight. Right, my apparent weight is 0, right, because that's what the scales are trying to tell me. I know that I have still got 686 newtons of weight. However, the scales can't help me with that anymore. I'm not sure if anything can help me. Okay, so there's question 1 from page 165, and it looks at that's a very classic question in physics, which is the scale question. If I move up and just look at one more question from the homework, I'm going to look at question 35 from the homework. Question 35 on page 183. Okay, again, as usual, silly question. I've got a person A standing here, and person A has a mass of 84 kilograms. Now, for some strange reason, it's saying that there's a person B standing on the head of person A, and person B here has a mass of 50 kilograms. So this person's A, this person is B. Oops. Come on. Okay, so the question is, what is the normal force acting on person A? So if I was to separate person A and say, what are the forces acting on person A? Well, here's person A, and I know that the planet is pulling me down. I know that there's a force pushing me down because there's something on my head, which is the applied force because of person B standing on my head, pushing me down. And I also know that the floor is pushing me up. Okay, no elevator and no bathroom scales here. Okay, so there's person A, and person A is experiencing those three forces. Now, if I do an F net equals, what are the three forces? FB plus FG plus Fn. Those are the three forces. Now, I know that the force of gravity acting on this person is their m times g. They are 84 kilograms times 9.8. Just move this up a little bit. And I'm getting a downward force of 823 newtons. I know that person B is pushing on me because of their gravity, the mg for person B. And I know person B was 50 kilograms times the 9.8, and I'm going to get a gravitational force for person B pushing down on me with 490 newtons. Okay, and that's all I know right now. Except I also know that F net equals ma, and I know that the acceleration is 0. This person is standing there. So this is going to be equal to 0 because the acceleration is 0. Now I can put the forces together. The force of B pushing down on me is negative 490. The force of gravity pulling me down is negative 823. Oops, 823. And the normal force, which is unknown, which I'm trying to calculate. So my Fn, let's take those two negatives across as positive and add them up, and I get a normal force of 1,313 newtons. Right. Now, the B part of the question, because this question isn't silly enough yet, the B part of the question says, let me get rid of some of this stuff up here. B part of the question says, person B up on top there is going to be given a helium balloon, and the helium balloon is going to attach to person B on top here and pull up with 300 newtons of upward force because of the balloon. Right? So, if I look at what the forces are acting on person A down here, right? Almost everything has changed. It's the same here. Fg is the same, right? The mg for person B is the same, but the force of B is not just mg anymore. There's also a balloon force giving person B a lift of 300 newtons. So if I was going to say what is the force of person B, it's going to be 490 minus, it's going to be, I guess, negative 490 because it's a downward force, plus 300, which is the upward force of the balloon pulling on the person. So B is only pushing down on A, person A, with 190 newtons now. So now I can take this number here and turn it into 190 newtons, and this becomes 1,013 newtons for part B. It just says what happens to the normal if you give the guy on top a balloon. Okay, so those are all normal forces, and normal forces are a huge part of what we're going to talk about today, which is friction. So section 5.5 in our textbook talks about frictional forces. So friction is exactly that. Friction is a force, and it has direction. Now, when I'm looking at the direction for a frictional force, the direction always says, look at the picture and pretend there was no friction. And if there's no friction, what direction is that object going to move? Once you know what direction that is, friction is in the opposite direction. Okay, so that's how you have to determine the direction for friction. So pretend that there's no friction, and then say what will be the direction if you have friction, because that's going to be the direction that friction is going to work. Right? It's in the opposite direction. It's in the opposite direction to that direction of motion, if there was no friction. And you think, well, that sounds pretty obvious, but you'll see as we get into this that maybe it's not always that obvious. Now, to determine how much friction there is, there are two pieces to this. If I was trying to pull a sled right across the snow, and there's nobody on the sled, and here's me walking along pulling the sled. Okay, it's pretty easy for me to pull. Right? Now, if I put a big block of ice on here, it gets harder to pull. And if I put another block of ice on here, it gets harder to pull. And if I take another block of ice, it gets even harder to pull. And the reason why it gets harder to pull is because I'm pulling more weight, right? Well, actually, it's not. The reason why it's harder to pull is because there is more normal force. What causes friction is not gravity, right? Well, it is gravity. I'm taking more and more and more gravity, and it's creating more and more and more. Remember, this is my FA here, pulling the toboggan. Let me get rid of my 5.5 here. And my frictional force is this way, right? It's opposing the motion. F, frictional force. It's opposing the motion. So again, pretending there's no frictional force there, which way is it going to go? It's going to go right because I'm pulling on it. So, which way is friction? It's left. It's the opposite direction. So, the magnitude of that force, okay, is determined by two things. Okay, first off, It's the amount of normal force. So if this is a 10 kg block of ice, and this is a 10 kg, and this is a 10 kg, and let's say the toboggan is 10 kgs, and the FG here is 40 times 9.8, or 392 newtons, then I know that there's a normal force of 392 newtons, because the toboggan isn't going up or down. And if the planet's pulling down with 392, I know that the ice and the snow is pushing back up with 392. Okay? It's not this that creates friction, it is this that creates friction. Yeah, but they're the same thing. They are in this question, right? But as you're going to see, in a lot of situations, they are not the same. So the question is, which 392 do I use to calculate friction? I need to use this one at the top here, right? The normal force is the one. Okay, and you're going to see again why as we get into this. Okay. The second thing that decides how much friction there is if I'm pulling this thing across the snow and it's sliding pretty easily, and then all of a sudden I've got to drag this thing across the road. It gets really hard to pull it across the road, and then I get to the far side, and then it gets easy again to pull. Okay, and the reason why it got harder to pull is because the contact surfaces here, right? The road and the toboggan are much less, there's much more friction there between them than there is between the toboggan and the ice or snow. So wood on snow slides pretty easily. Wood on cement or asphalt does not slide very easily, and I need to have, there will be more friction there, right? Which means that this force here is going to be different depending on what surface I'm on. Okay, so those are the two different things that are going to affect friction here. Now, the formula that we use for calculating friction is this one here. Friction is equal to, the symbol there is called mu. Again, we've got lots of, we've got alphas, and we've got betas, and we've got gammas, and we've got pi, and we've got delta, right? This is mu, mu, all right? And it's one of the Latin letters, and it is our coefficient of friction. And what it does is it tells me the ratio of frictional force, it tells me the ratio of frictional force to normal force. Okay, for the amount of normal, more friction means it's harder to pull, less friction means it's easier to pull. Big value for mu means it's harder to pull, small value for mu means there's little friction between the two surfaces. Okay, so to make this a little bit more complicated, let's get rid of all my symbols here. It turns out that there are two types of friction. There's a friction that exists between objects when they're not moving. That's called static friction. Static, stationary, stationnement. If you've taken your French classes, stationnement is parking. So static friction is for friction for parking. It's for friction when an object is not moving. So let's say you're trying to pull something across the floor and it's not pulling, and you're pull, and it's not moving. All of a sudden, oh, it starts to go. Okay. Once it's moving, it now has a different type of friction called kinetic friction. Kinesis means motion, right? Kinema, cinema means motion pictures. Kinetic forces mean talking about friction, which is between objects that are in motion, sliding over top of each other, right? Not rolling, but sliding. Now, when objects are, again, if you think about trying to pull an object, if you were trying to move a heavy object, let's say you're trying to move a big appliance across the kitchen. You've got damage behind the stove, or something fell behind the stove, and someone says, can you pull the stove out? You go and you pull it out, and you're pulling and pulling and pulling. It doesn't move. You say, okay, you call your sibling over, and you say, okay, the two of us now are both going to pull together, and you get everything out of the way. You say, all right, pull, and all of a sudden it starts to go. And as soon as it's going, you go. You'd say, don't stop, right? Because once it's moving, it has changed from static friction to a lower friction, which is kinetic friction. So the static friction is always higher than the kinetic friction. Now, if I look at the values for mu, there are some sample values. You can find these all over the place, but if you look at, let's say, steel on ice, so maybe this would be skates, right? Moving before you actually get to start it from moving, or say it's a toboggan with steel rails on the bottom, right? To get it started, you have to overcome the mu s here, the stationary friction, and then as soon as it's moving, there's 10 times less friction. Right? If I have rubber on ice, right, there is your snow tire, your wheels on ice. Again, if I'm trying to pull my toboggan, my wooden toboggan, and get it started on dry snow, it takes that much kinetic friction, static friction coefficient, and once it's moving, it's easier to keep it moving. If I'm on wet snow, again, it's a little bit easier to get it started, and then once it starts moving, it's even easier to keep it moving. So notice that our values here, we even talk about, in biophysics, we talk about the physics of blood flow, laminar blood flow. We talk about the physics of motion in joints, right? And there's friction in joints, which is why joints often need some repair, maybe surgery, maybe replacement, right? Knee replacement, elbow replacement, shoulder replacement, right? All these things, hip replacement, happen because we have friction going on there, and we need to fix the joints because they've been damaged. Okay, so I'm going to use the same formula that I had up here. Friction is equal to mu times the normal, right? And then depending on whether or not it is static friction or kinetic friction, I'm going to use this formula down here for static friction, this one here for kinetic friction. Right? Now, usually in a question, it will just tell you the coefficient of friction here is whatever the number is, right? And we're not going to worry so much about having to look up the values. I'll just tell you what the answers are in the question. Now, if we look at the samples here, 8 to 12, so there's a whole bunch of samples. I want to take some time and go through these, because I think you'll find as you go through these, friction is actually pretty straightforward for the most part. Okay, so let's look at question 8, sample 8. Okay, sample 8 has a person pushing a lawnmower. Okay, and it says the lawnmower has a mass of 12 kilograms. It's being pushed by a force which is, okay, so here's the lawnmower. So this is, come on you, sample 8 on page 167. So here's my lawnmower. And it's being pushed with a force, right? The force is The force is 150 newtons horizontal and 40 newtons down. So the force is 40 newtons down and 150 horizontal. So there's the direction of me pushing on the lawnmower. We're told that it's a 12 kilogram lawnmower, and we're being told that it is the kinetic coefficient is 0.9, and the force of friction, it says find FF, find the force of friction. Now, I think in here it should be telling us that the acceleration is 0. Okay, so yeah, it doesn't say it in the question. I'm just reading it now for the third time, and it's not telling me anything about the motion of the lawnmower. I'm going to assume that the lawnmower is moving forward at v equals constant. In other words, there is no acceleration. So that's an important piece for us, right? Now, what I also know is that there's a normal force, a gravitational force here. You can almost always just put your gravitational force in before you do anything else. And I'm getting 118 newtons of gravitational force. Okay. Remember back on the question, it told me how much horizontal and how much vertical force there is. We were told that the 40 is down and 150 is this way, and 40, I can't even write it in here, 40 is my down force. So, we're also told what the value is for mu kinetic, because it's moving, it's rolling across the lawn, and the mu value is 0.9. Okay, so what we're looking for is the frictional force. And I know that the frictional force is equal to mu times the normal. Okay, so I need to know mu, and I need to know the normal, and I can calculate my missing frictional force here. Now, this isn't quite as simple as it looks, because when I think about the normal force, let's just draw the free body diagram for the lawnmower here. Okay. If I say, what are the forces acting on the lawnmower? I'm pushing the lawnmower forward with 150 newtons, right? And I am pushing down, maybe it doesn't have zero velocity. I'm pushing down on it with 40 newtons. I am pushing, it is being pulled down by the planet by 118 newtons, right? So I can calculate the normal force. This was FA. This was me pushing on the lawnmower. Remember, I'm walking behind it. My arms are pointing down towards the handle, and as I'm pushing the lawnmower, I'm pushing it forward and down at the same time. So if I look at all my forces here, my normal force if I look at the vertical components here, there are three forces acting in the vertical plane, the up-down plane, right? Three forces. And those three forces are going to be the net force in the vertical plane, 118 for gravity, 40 because me pushing down, and then the normal force here going up. Okay, so those are my three forces acting in the vertical plane. Now, if I know that it's not moving up or down, right? It's got zero vertical motion, then the acceleration in the vertical plane is going to be zero, right? 12 kilograms times acceleration of zero. And I know that the normal force, well, I don't know the normal force, it's unknown. I do know gravity is negative 118. And I know that my force pushing on the handle is pushing down with 40 newtons. So my Fn now is going to be equal to 118 and 40, 158. It becomes positive on the other side. So the friction, normal force is 158 newtons, which is an upward force. Now I can go back and I can calculate my frictional force way back here because I know mu times the normal. So let's just go back down. So now I know my normal. I can calculate my frictional force, 0.9 times the normal, 158. Now notice that (142 newtons). Notice the direction here, right? This is a really important piece, right? The direction is in the opposite direction to the direction of motion. Again, pretend there was no friction here. I'm just pushing forward on it, right? It's going to go forward. Now I add friction. Friction is working back. Notice that the direction for the normal force was up here. right? So I have an upward force on this side, and I have a left force on this side. So notice that the direction here will not be the same as the direction here, right? That's one of the things about friction that we always have to be thinking about, is how do I determine the direction for the frictional force? Okay, so I've determined the frictional force. Okay, question 9 says, having solved for F net in the y direction, we can solve for the rate of acceleration of the lawnmower. Oh, I guess it doesn't have zero acceleration. I didn't read far enough ahead. So let me get rid of some of this stuff. Acceleration is not zero, and the v is not constant. Okay, so let's roll back down, and let's say, okay, let's look at this lawnmower now. Here's the free body diagram again. Right, I have forward force of 150 newtons. That's me pushing. I have a backwards force of 142 newtons because of friction. I'm going to not worry about the ups and downs anymore because it's not going up or down. I'm only going to worry about forces in the horizontal plane now because it's moving in the horizontal plane. So horizontally, the F net is equal to FA plus FF. There's two forces acting in the horizontal plane. Now, I know that the F net, is MA. Applied force is 150 in the positive direction, plus the frictional force of minus 142 in the backwards direction. I know that it's a 12 kilogram lawnmower. 150 minus 42 is 8 newtons, so the acceleration is 0.67 meters per second squared. All right, so we're now, again, we're using our free body diagrams. We're now including friction. We're calculating friction into our questions so we can come up with what is going to happen to this object. Now, another part of this question would say, if this lawnmower was moving at 1 meter per second before I started pushing, what would be how far would it travel in, I don't know, in 10 seconds, right? And we could calculate a delta D. All right, so there's all question sample 8 and sample 9. Okay, let's look at sample number 10. This is question 10 on page 169. Okay, it warns us this is a twisted question. I'm not sure. Two people are pushing horizontally on a crate of mass 50 kilograms. One person is pushing from the right with 50 newtons. The other person is pushing from the left with 80 newtons, and the coefficient is 0.3. Find the acceleration of the crate. Okay, so here's my crate sitting on the floor. Planet's pulling it down. The floor is pushing back up. The person is pushing left with 80 newtons. Person on the right is pushing to the left with 50 newtons. Let's fix that up. Come on, you. 50 newtons. My stylus is not helping here today. And it's a 50 kilogram crate. Right, so those are all my forces. This is an applied force. This is an applied force. We're told mu is 0.3. Okay, so let's look at what we can calculate. If I'm guessing right off the top, if there's no friction, which way is this crate going to move? It's going to move left, right? Because it's going to move right, because I've got a greater force to the right, 80 newtons, and only 50 newtons pushing left. So it's going to move right. So if there's friction acting here, friction is actually going to work in the opposite direction to the direction of motion. Again, so notice how we were doing our direction for friction. Look at what direction the object's going to move without friction, and then say, okay, friction's going to be the opposite direction. Now, to find friction, I need to know mu times the normal. To know the normal, I need to know gravity here because there's equal up and down forces, and to know gravity, I'm going to use mg. So I'm going to take my 50 kilograms times 9.8 newtons per kilogram, which gives me 490 newtons of downward force, which means gravity, the normal force now, is up with 490, which means the frictional force is 0.3 times 490, and 0.3 times 490 is 147. Oh, I'm seeing how this is twisted now. So the frictional force is 147 newtons. Now, if I do an F net statement, F net's going to give me F net in the horizontal plane. It's going to be 80 to the right, plus 50 to the left, plus friction, plus friction, which is 147 to the left. I end up with the net force, which is 197 plus 80, negative 117 newtons. Right? And F net is MA, and it's a 50 kilogram block, so I can calculate the acceleration. Let's just move this up a bit. The acceleration works out to negative 2.34 meters per second squared. So this crate is going to accelerate that way at 2.3 meters per second squared. Now think about it for a minute. If this crate is having a force applied to it of 80 newtons this way and 50 newtons this way, so let's say I got a stronger person on the left and a weaker person on the right, or pushing right, is there any way this crate is going to accelerate left? There's no conceivable way. Right? The force of friction has a maximum value of the value that we put in there. So because the net force here, the net force here is 30 newtons to the right, if there's 150 back, friction doesn't cause acceleration. Friction can only resist the motion. So the acceleration here of this crate, is actually going to be 0 meters per second squared, because there's just not enough friction to overcome, there's not enough applied forces to overcome the frictional force, so friction is just going to basically shut her down. Okay, let's look at question 11. Sorry, this is a long one, but again, there's only 3 notes in this, but they're all a bit long. This one's the longest. Chapter 11 says, let's look at what happens. I'm going to push a 5.5 kilogram block up the wall, and we're going to look at the forces here. Okay, so here's the 0.5 kilogram piece of wood, and I'm going to push it up the wall. Now, it says the forces that I'm going to apply to this block, it's a 0.5 kilogram block. Applied force is 6 newtons upwards. Okay, let me just slide this down a bit here. Let me get rid of some of that stuff from before. Okay, so I'm pushing on it with 6 newtons up, and I'm pushing on it with 2 newtons towards the wall. So my force is actually this way and this way. So I'm actually pushing the block that way. I'm pushing it towards the wall and up the wall at the same time with 2 and 6 newtons. Okay, so those are my applied forces. Okay, let's get rid of all that. Now, let's look at what else I know. I know that there is Fg. You can always do this first before you do anything else because you're probably going to need it. So gravity's pulling it down with 4.9 newtons, and now there's friction. Now if I look at these forces here, let's not add friction in for a minute. I say, which direction is friction going to work? Well, the block, this force here is not going to push it into the wall, right? It's not going to go through the wall. So I know that there's a force pushing back this way, right? Remember, perpendicular to the contact surface is the normal force. Okay? And I know if there's 2 newtons going left, I know the wall is pushing back with 2 newtons. Now, the left-right forces cancel out. The up-down forces leave me with a net force up the wall of 1.1 newtons. I have 6 up and 4.9 down. So what direction is it going to accelerate? It's going to accelerate up. So which way is friction going to be? Friction is down. And friction is equal to mu times the normal. I know that my mu here in the question is 0.4. It's the coefficient of kinetic friction, times the normal force, which we know is 2 newtons. So my frictional force is 0.8 newtons. So now if I look at my total up force is 6. My total down forces are gravity plus friction working against the direction of motion. So if I'm going to do an F net statement now, again, I'm only looking at the vertical motion because the horizontal motion, the left to right, is going to cancel out. So the up-down motion, vertical, is equal to plus 6, which is my up force, plus my gravitational force, negative 4.9, plus my frictional force, negative 0.8, because remember friction is working down. F net is equal to ma. 6 minus 5.7 is 0.3. Mass was 0.5. So the acceleration is 0.6 meters per second squared. And it's positive, so it's going up the wall. Okay, so notice the difference in this question. The direction for my normal force here now is not down. It's not opposite to gravity, right? Where before I might have said gravity is what causes friction. Well, the gravity's not got anything to do with friction here. If anything, gravity's working with friction. They're in the same direction. So remember, it's the normal here that's responsible for determining friction. Okay, and then the very last question in chapter 5.5 is sample number 12. On page 171, talks about a hockey puck. A puck is 0.7 kilograms sliding along an essentially frictionless patch of ice at 6 meters per second, and then it comes across some rough ice where the friction is 0.10, and how long is it going to take for the puck to stop, and how far is it going to travel? Okay, so here's my hockey puck. And it has a mass of 0.30 kilograms. Okay, 0.30 kilograms. Right, and now I know that it's moving in a certain direction. Let's say that it's going this way. Come on. At 6.0 meters per second. Now, if I look at the forces acting on here, right now I have gravity, 0.3 times 9.8, which is 0.29 newtons. Now, it's going across the ice, So the ice is pushing back up, creating a normal force, 0.294 newtons. So I've got equal up and down forces, and now I know if there's no friction, it's going to continue moving to the right, because that's the way it's moving. Nothing is pushing or pulling on it until it hits the rough ice, and now it's going to get pushed back by friction. Friction's going to slow it down, right? To calculate my friction, I'm going to use mu times the normal. Mu is 0.10. It's not a very high amount of friction, but again, it's just on ice, even if it's a bit rough, times 0.294 newtons, and I get a frictional force of 0.029 newtons. So I now have a frictional force, and if I say, what is my F net now? There's only one force acting on this. That is friction. Right? There's no other force in the horizontal plane. My vertical forces, 0.29 up and 0.29 down, have canceled out. So the only force acting is that 0.029 newtons pushing back. Oh, I'm sorry. I've got... This should be 2.9 newtons. 2.9 newtons. And this is 2.9 newtons. And this, got ahead of myself here, is 2.9. And this is 0.29. I've added an extra decimal place into all my math here. Okay, so the F net is equal to the frictional force, which is in the negative direction, and it's 0.29 newtons. F net is ma, which is 0.3 a. So I can calculate my acceleration, 0.30. Acceleration is 0.29 over 0.3, which is negative 0.97 meters per second squared. So now I have an acceleration, and now it's going to come to rest. And the question is, how far will it travel, and how long does it take? Okay, so let's just look back at my question here for a minute. Notice that it was going at 6 meters per second before it hit the rough patch of ice. So that actually turns out to be my V1. That's my starting speed. And when it gets to here, it's going to have a V2 of 0. It's going to come to a stop. So let's go back and let's look at some of our questions here now, some of our data. I'm trying to calculate delta t. How long is it going to take? It's going to be V2 minus V1 over A. Right? V2 is 0 minus V1 divided by A. And I'm getting a time of 6.2 seconds. And then the question, other part of the question says, how far will it travel across that rough ice before it stops? I'm going to use V2 squared minus V1 squared over 2A, because I know V2 from the question, V1 from the question, and I've just calculated A. If I use the time, it means I've used A to calculate T, and now I'm using T to calculate D. Let's not do that. Right? So I'm going to choose the one that's going to maybe give me the least amount of error. V2 was 0 squared minus 6 V1 squared over 2 acceleration, negative 0.97, and I'm getting a distance traveled of 19 meters. All right, so we've gone a long way in one period, right? We now know how to calculate friction, and once we've calculated our friction based on mg and or Fn based on Fg, again, it all comes back to our free body diagram. All right, so I'm going to leave you with the questions here on 130